Hello and welcome. I'm Bill Wake. We're at the end of a fairly long project for evolutionary design, and as part of a bigger project with a basic interpreter, we took our basic interpreter from a recursive descent parser to this parser combinator approach, and we're basically at the end. We got a couple more to-dos where we liked our old messages better and we want to get something more like them. And other than that, we got to do a little work on the parser combinator library and a little work on the compiler, and I think we'll wrap it up today. We were in the middle of this to-do. We're not getting the message we want. We'd like expected start of expression, but we're getting expected character not. We could fix the wording on that, but the not is the token. So we know we're messing up on the token rule. On the matching rule, sorry. All right, what we've done so far is we commented out most of the factor, so we only handle parentheses and numbers right now. And we're trying to do a test. It's really an error message test if you don't give it a number, okay? It could be other things, strings and so on, but to simplify this, we did a pretty extensive tracing the other day, and I think we know we're somewhere in here, like we're getting this a complaint that we don't match a not. And it's like, well, that's not required. Okay. It's a Boolean expression. It could just be relational expression, and that's what we expect. All right. And I tried switching these, but I switched them wrong. So I think I can do it better today. Let me try again. We're going to pull relational parser down, and then this. And the mistake I made was I tried to swap the first couple lines only and not the make unit expression, but make unit expression is really tied to the nots, so that's actually should be better. So the only reason for this is it's kind of like, how does it report errors? Well, it basically, with an or, it reports the last error it saw, and if it didn't match a relational parser because of that star, then we try and match the not. Well, it's not a not statement, so it doesn't have a not, and that's not an error. Now, in the grand scheme of things, it would bubble out and work, but in this way we're working, we've explicitly put some sequencing in. So if you look at it from a grammar perspective, these two were the same, whether I did relational first or match one not. If you look at it from the operational point of view, we're saying we're privileging the second of alternatives. So the last alternative gets the privilege. If there's a tie, its message dominates. And I think it's silly to say you didn't match a not, because why would you? It's like, that's kind of arbitrary. Start of expression is definitely better. So I think swapping these will give us a different message, okay, because of that ordering. So let's run this test again. And I have my suspicion. I think minus is going to have the same treatment, need the same treatment. Yep, missing minus. Okay. Minus is another one that's allowed to be the start of an expression, but it doesn't have to. Okay, so let's clarify our rule here and swap the order. And this thing of dealing with the error messages, it really is, it's kind of the difference between writing a compiler that's a product and talking about grammars mathematically. Like in the compiler product, we have to worry about error checking and all that. Nobody wants something that says your program had an error, no indication of where, so managing that puts an extra layer on your grammar stuff. And sometimes you make these kind of changes. And actually that gives us a bit of a pattern for the unary operators, which is fine. All right, now I think we're ready to see what really is going on. I don't know if we'll get the right message or not. Oh, we do. Oh, so we may not. I was worried we would need to backtrack on the star. Okay. Well, we got our desired result, so I should take the win. We should still see a bunch of failures because I commented out all that expression stuff. Yeah. Okay. There's people that are really assuming they're going to have that. Okay, so let's take this off and this off. Okay, and run those tests again. All right. No filter results. Why can't I see my tests? 296 tests ran. Let me try that again. Product test. Oh, I'm only showing failures, I think. Is that right? What are these? Oops. Show only tests in the currently active test plan. Only failing tests. I don't want that. Only skip tests. Okay. That's better. Okay. Let's see. So that remaining to do tests. Okay, so we did one of them anyway. August 23rd. Let's see. This was the error for this. Now is expected start of expression. Okay. That missing expected character thing, I'd like to change that. Oh, we got another to do, I think, if I remember. To on missing line number after comma is error. I think that's probably okay. If it's pointing here and it says missing integer, I think that'll be okay. The only question I have is integer. Let's see. Do we have a? Where's that message come from? Excuse me. I think it's coming from the name then. Let's see. Let's open token match. Okay. Oh, there's this. Integer gives integer. I think. Let's look around. Integer may always be a line number by this point. No, it won't. Okay, this is definitely worth a look. Okay. There are a lot of places we match integers. Line numbers required at start of statement. Okay, that's a good match. It'd be nice if the message I wish I had here. No. Where's that to do? This one. Okay. It would be nicer if it said missing line number. And this is the on go to statement. Let's take a look. On statement. Let's find his parser. On parse. A lot of expression parsers. Well, they're kind of alphabetical, aren't they? If input next on. Okay. Match one on. One of go to. Match one integer. Oh, yeah, I guess it would be nice to have this. I mean, that's a little bit overwrought, but I think maybe this is makes me think there's another test to write. Oh, no, we can't write that one. I was thinking, what if you just left out the commas? But the way BASIC works is it sort of like smashes, it skips all spaces. So if you had 10, 20, it would look like go to 1020. But, whoops, the message we're getting is coming from here. And I think we could say expected line number. Match one. Let's see, match. Well, we did that here. Match.integer. Oh, it caught up. Okay. And actually, I'm sort of wishing I had expected line number. So let's change the test. We're getting missing integer. We know that, so I'm not too worried about it. My order of TDD is a little off kilter there. Okay, that's all that took. So, statement parser. I don't think we need this. Oh, I guess that would be if we did on go sub and no line numbers at all. Do we have a test like that? Okay, I guess we don't. Let's do that. On missing on without any line numbers is error. And I think if this is doing its I don't know, that message is a bit much, but it's what I think we're supposed to be producing now. On statement requires comma separated list of line numbers. I don't know if it really does. It could conceivably be legal without it, but we're saying there must be one. Okay. So this test, I think I did go to. Let's do go sub just for variety. Okay. Good. All right. Okay, so now I think our to-dos is only in our message files. Okay. This is good. Okay. Now we have this missing expected character. I'd like to change that, and I'm going to do it backwards again. We know where that is coming from. It's in Token Matcher. Down here somewhere, match one, expected character. I think the word character is misleading because it could be lots of things, and this I'd like to just put the word in quotes. So we had missing not in our test at that one point, and it just said missing not, and it's like, what? So at least quoting it will kind of indicate this. And then expected token type, it'll say expected integer or variable name or whatever. And presumably some tests will break because of this. Oh, and I haven't checked in. Waking up slow this morning, I guess. Okay, and let me undo that and check in. It differed because of the parser combinator library. Okay, so that's good. Take this out. Missing. Not. I guess I could make this capitalized. Seems more natural. No, a number of tests will fail. Mostly expression tests. Missing left paren. Did I do that backwards? Oh no, I haven't done it yet. Expected. Oh wait. Wait, what? Missing left paren. Okay, let's find that predefined function. Expression parser. Match one is in our token matcher. How did... Oh, I'm backwards, aren't I? Token type or expected this. Okay. And this is the one that uses the description we have on file. Okay, so if we don't have it in our list of token matching, these names, then we just print the stringification of token type. It might be nice to make all the tokens have that, but I think this will be adequate. Okay, so now we should get some different failures. Probably more failures. We had 5. No, wait a minute. Well, missing token description should be fine. Oh, we may not be using the, we may not hit this. Let's test, let's put a test in token matcher. I don't think we even have one yet. Okay, let me, I'm going to alphabetize these. I don't know, there's a setting somewhere that does it, but I seem to have got it on some files and not others. Okay. We don't have a token matcher test. These were all kind of extracted functions, but let's make sure. Let's add one. Okay, and this is token matcher tests. Okay. Well, okay, so we're saying token matcher. So I guess we're going to do a match one.parse on something not in the list. Okay. So, is that a, it's just a function on the token matcher. Okay. Match one, and we'll do token not, and we will assert, this is dot parse. Okay, and then expression one, we expect to see missing not. Oh, whoops. Too smart. Not there. This parse, what does it want? It probably wants real tokens. Okay. Line, column, type. Okay. Line 1, column 2, type is integer. Okay. Match this. Cannot convert parse result. Ugh. It's annoying. Let's see. Expression plus test. And that's a little helper. REPL test. Okay. Let's see parser statement tests. I think we've got check failure. Check error. I'm not sure the best place for this to live, but it's kind of what we want. We want to give it a string. Well, no, it's not. We're trying to get to one specific parser. I mean, it's kind of what we have to do. All right, let's... I hate to make this test more complicated. Okay. Guard case dot failure. Let position, let message. Otherwise, it failed. Should return failure. This equals result. All right, let's get it working, and then we will deal with it. Okay. The position is 0 because we're at the front of the list. And the message should be missing not. Okay. Well, I guess that's... Oh. Okay, good. I think missing expected not is not equal to... Yeah, okay, so where's token matcher? Oh. Okay. I think, okay, that should pass now. Okay. And then, is the right word missing there? I'm going to say it's expected. And there's a bunch of tests that'll break, or at least a number of tests. Yeah, I think that's a better wording. It's hard to get these just so, but all right. So improve error messages when token not matched. Okay, let's see, where are we on the list of things? Expected character missing XYZ. I guess we're saying that should be expected XYZ. Now, I had fully expected to have to do some variations on these, but I don't think that's the case. All right, so I think we're not going to do these two. They're nothing to do with the parser. They're more how we define the interface from the lexer to the thing. And then this one is a missing. It should say you can only dimension by an integer type. So I'm not going to worry about it here. Our goal was evolve the parser more or less refactored. We had a few changes, but basically the error messages, we've changed those now, but we weren't enforcing new rules. So I'll keep that on my list of things I should do sometime, but it's not critical for now. I do want to do some cleanup in the tests. I feel like there's something going on there. Let's see. I'm pretty sure we had duplication across these things. Okay, so check expression. Let's see. Let's see if that shows up multiple places. Yes. Okay, and I think it's going to be the same code. This is expression tests. Oh, thank you. Okay, 10 print. Syntax analyzer assert equal 10 print expected new line. 10 print syntax analyzer. Yeah, these are the same. Okay, and I guess it seems to be mostly on the syntax analyzer. I don't know if we had a... Okay, so what I'll do... I'll make a new Swift file. And this will be a test support. So syntax analyzer plus test. All right. I'm going to pull these methods over there. And this is going to be an extension. So this is one of the techniques I kind of like. I'll probably write it up for next month. But I'm making an extension, but it's only showing up in the test folder. So these are things that they're useful. They're useful in testing, but they're not thing I want to include in the real one. Cannot find type. I think we just need it. I guess we'll need that too. Okay. Import XC test, import BASIC. Okay, that should help that. Okay, and then let's get this function. Check expression. Well, what's a good way to do this? Well, we're certainly going to do take the whole function. Okay. So now I can say parse. Let's see. What do I want to say? Maybe it's not the right place. could I say expression.check? Let's try that. I think expression's an enum, so it's a little funny. That's okay. So if I say expression, all right. So let me try changing the test here. I'm going to say expected dot check expression for now. Expression expected, and see if that all works. Okay, so we can improve it, but let's just see if this goes. We're looking at expression tests. Should be working. Okay, probably could have just run those. All right, so now let's see. Where's my checks? Okay, we have to check expression. I think we're saying predefined. It almost feels like it's backwards, doesn't it? Maybe I should put this on string. A little weird. Okay, so if it's on the string, it goes the other way around. Expression dot check. Expression. Okay. Again, this should work for this class. Okay. And I'm gonna call it check parse. I guess rename probably would have worked. Check parse. And I'm just going to take expected. Expected. And then expression is self. Okay, and the test is expression.checkParse, like that. Okay, and then the file should change name if it's going to be on strings. Error string expression check parse expected. I guess check error, check one statement. Okay. Can I? Yeah. I don't know if that's better or not. Yeah. Okay. All right. Is that? I think it's okay. It felt weird to make up on syntax analyzer because we don't really have one around at that point. We really are starting from the strings and checking that they get the right parse. Okay, let's find the other place. This one. Okay. I think That's an improvement. Let's make this, rename it string plus test. Okay. And then what else do we have common? So check expression, check error. Let's pull that. Check error, program string. Okay. And this is going to become program.checkError program expected. So kind of the small step version of that change. Okay. And then this argument's redundant. Program. Expected string. Program is self. Okay. And oops. Expression test. Where's my other parser expression test? Does it do check error? Yes. Okay. Well, theoretically, it's not that much slower to run everything. This is fine. Okay, I think that one's better. Expression parser. Whoops, expression parser test. Expression test. Check error. Check one statement. I guess this could be check statement. Keep going the wrong way. Okay, and so this is program.check statement. Let's just put what we know we're going to do. And this is okay. Let's see this one first. Who uses that here? Def call. Okay. I suppose. Oh, it's a couple of them. Fetch from array. Okay. And parser statement tests has check statements. test check statements becomes program dot check statements expected. And check error. This one actually looks different, doesn't it? Case error. Parse, why is that different? Check error. Oh, that is more similar than I remembered. Okay. Syntax analyzer parse line. Output statement 0. Actual. Yeah. Okay, that looks like the same. Program dot check error expected. Okay, so I don't know. Let's see. Does this? How would this read if you put it in line? So check one statement. Do 10 remark dot check statement. Skip. All right. So I'm okay with how we have it. I think it's a little awkward. But I'm okay. This one's kind of sort of a parameterized thing. Yeah, I think that's okay. If input, see, they are let. Okay, yeah, we did kind of alphabetize these. Print. Okay. Let's check in. Reduce duplication across tests. Okay. Well, we've come a ways. I think we are officially done with our to-do list. Last thing we did was reduce duplication across tests. And that was using an extension on string, which I don't really like to extend system classes, but the scope is kind of bounded being in the test area. I think it was the right thing to put it on. Okay, so I think what I'd like to do is just do a quick review of where we are on this thing. So the expression parser now, it's the bulk of it is in this make. Make produces a parser that goes from tokens to expressions. And you do this, basically the way you write the grammar is kind of bottom to top. Is if you have to reference something in the future, it gets a little more complicated. So here we've got expression parser. We had to set that up already. So it's defaulted to a bind. But otherwise, it's easier to reference the earlier ones and the later ones. Grammars tend to be more top-down, but it's, I guess it depends which way you like going concrete to abstract or vice versa, maybe. Okay, so we've got these built-in, well, they're not built-in. We wrote them, but we've got simple matchers that match single tokens or one of a set of tokens. And we have more complicated matchers, parsers that match complete expressions. And we're using these combinator operators that let us make grammar rules. So This one is a sequence rule. It says you match a left parend. This one says match in sequence, but ignore the one on the left, and then match an expression, and then match in sequence, ignoring the one on the right, which is a right parent. So we don't need the parentheses in our representation of an expression, so we can ignore those in the grammar. And a normal grammar doesn't bother itself with that kind of detail of what gets ignored. Okay. We can match numbers, and this one says feed it into this method, so it produces, it just calls the enum constructor. Same thing for integers and strings. And then we get into our remaining factor types. You can have predefined functions like square root, and you got a function name match the left parenthesis, expression match commas, as many as you want, comma listed, and right parend, and then pipe it to a checking call, pipe it to something that makes the thing. Okay. And we work our way up. So there's all the possible factors, parenthesized and so on, variable. We can put messages in. If none of these match, then we wanted expected start of expression. Then we get into the precedence. We have one parser per precedence level. So power feeds off factors. Then you can have negation on the powers. Then terms, which is times or divide. And sub-expressions, which is plus or minus. And relational operators. And Boolean not, Boolean and, Boolean or. Okay, what is that? 8 or 9 levels. Okay. But the result of the whole thing is we have a parser function. We bind that in as the expression parser. And now we have a expression parser that can be recursive because it calls parenthesized expressions inside it. Okay. Then the rest of this function is all the semantics. So, that's about, 100 lines of grammar. And then all these things that say, what do you do for certain situations? Check predefined. We want to make sure that it has the right number of arguments. If it doesn't, we append a missing argument because some of them are optional. And then we type check it and check success or not. Okay. And make unary expression and so on. So the rest of these, they're all the things to check and make expressions. Statement parsing is very similar. There's a little bit of setup, but then basically you have assignments, data, def, and actually let's go the other way around. Let's start at the bottom. Okay. A statement parser is either a one-word statement like and or stop. It's an assignment, a data, define, dim, for, go sub, all the keywords that let it work. Otherwise, it's an unknown statement. And then the rest of those parsers, they're just there to build up each individual parser. So how do I do a read? Well, you got the keyword read, ignore it, a list of variables, and convert it into a read statement. Okay, very straightforward. And again, the rest of the file, I don't know when the grammar started. Well, it really is near the top, isn't it? Okay, so make started on line 53, and we had, 250 something. Yeah, almost 250. So about 180 lines of grammar, basically. And then the rest is type checking, all the functions that provide the semantics. Okay. So in our original, let's see, let me make sure we're checked in. Okay. And I don't think I had, okay. Final check-in. Optimistic, right? Okay. I'm going to go back. Let's go back to main. Okay. And I don't really care about to do. Let's check that out. Okay, so now there is no expression statement thing. There's syntax analyzer, I think. Is it called? Parser. Oops, look up here. Parser. Okay. So before we had this pretty large parser file, and let me find, well, we can see it here. Okay. So the semantics of a line is it must start with an integer line number, and line number has to be in a certain range. You have a bunch of statements, and at the end, you expect an end of line. Otherwise, you get extra characters, and we return a parse. So a parse is like one or more statements, a group of statements, I guess you could say. It's kind of the parser produces a parse. That's the whole statement and expression tree. And what you see is everything is kind of mixed together. So this matching is doing the grammar checking, just like this try statements and the require. Then there's other stuff that's in here to do the semantics, and other stuff to do the construction of the resulting type, and other stuff to handle the errors that if we're finding missing tokens and so on. So the contrast is the recursive descent approach we're using blends parsing, error checking, semantic errors, and producing things. Okay, so it's kind of blending 3 or 4 things. The parser combinator approach, it was much more. It was very separated, right? We had the parser. We provided a little bit of error messages like we did here in the parser, but the actual error handling we didn't deal with it. It was dealt with by the parser library. Okay, and then the semantics, we explicitly have separate functions that either apply error checking like this thing or produce the parse results. Okay, so it's kind of a contrast of approach. All right, so I think as a wrap up, I want to go through and just kind of start back where we were. The goal of this evolution project was evolve our basic interpreter from recursive descent to a parser combinator approach, and we've succeeded. I think it's totally converted. There's no real signs of recursive descent in there anymore. It's all in the combinator form. Okay, and so the approach we took was very evolutionary. We started with the original parser, and then we just evolve every step on the way we can release. I mean, we had to be back to a green test, but for the most part we were. Now, the way we did that was we provided some adapters that let the old parser call the new and the new parser call the old. And with both directions working, we could smoothly change out any part we wanted. So again, the difference here, you have a grammar expression goes to a term plus or minus term. So that's, 3 plus 2 plus 4 plus parenthesized 7 and so on. Okay. And you write a function for it, and the pieces of the grammar show up in the recursive descent routine. So the name maps to the name of the function. It's got a return type that's the result of what we're doing. The parentheses in the grammar rule said repeat 0 or more times. That corresponds to a while loop. And then we're looking for plus or minus. And once we match it, that's fine. And then we find term. We build up an operator, a binary expression from the operator, the previous result, and the current result. So it all maps. It's not hard to write recursive descent, but it all maps into some action in there that's either semantic or whatever. Now, we didn't deal with error checking in this one. Basically, it doesn't have its own error checking. It's up to term to error check things. And if there aren't any plus or minuses, it's like, oh, it's not our problem now. Okay. The contrast is, okay, so yeah, kind of said all The contrast is the combinator approach, the new way we did it. You have this grammar item, and then you translate it pretty straightforwardly into the combinators. In our case, term plus or minus term repeated. Well, we have this special operator ampersand for that. So the left-hand side maps to the left-hand side. When we got terminals and non-terminals, we reference the corresponding parser. So there's a match parser and a term parser. And we can use this separated by. So A separated by B gives you A, B, A, B, A, B, A, and so on. So term, minus term. Okay, all that comes from there. And the or else, well, A or B matches A or B, but if you had a C, it wouldn't match C. Okay. So in parser combinator, like a lot of that overhead has been pulled out. It's very abstracted from the recursive descent. But at the expense, we have to make a binary tree operator, but that was reusable across all the levels. So it meant we'd reduce duplication because the tree formation stuff is only done once now, defined once. Okay, so this approach really works nicely. I mean, it looks much more like the grammar, so it's easier to confirm to yourself that everything looks the same as it should, and so that part's nice. Okay, but I want to do some work on comparing these things. So just capturing notes and reactions on it. So recursive descent. The code is mapped from the grammar. Maybe transformed from the grammar. The parser basically is the grammar. Okay, it's much closer. All right. This one, we said it blends parsing, error checking, which semantics maybe covers that. I guess error checking, maybe this, let's say blends parsing, syntax error checking, semantic error checking, and construction. And then this one, parsing with syntax error checking in the grammar, and semantics and construction in separate functions. Okay, so I think that's kind of this core thing. Now, this is it was less code. Okay. This one is more code if you count the parser library. But less code specific to the interpreter. Okay, so I think the parser library is around 500-ish lines at core. I don't know. Let's see if we can. I think I have it here. Yep. Okay. No, it's more than that. But these things are all pretty small. I mean, each operator is pretty straightforward. 40, 50 lines. The exception is and then, because we had to define so many variations to cover types that match, types that don't match, types that combine an array with a not array. But each one of those is pretty small. That's the biggest. This is probably the biggest file, 250 lines ish. Okay. So yeah, it's, I don't know, it's 500-ish lines is probably a good guess, maybe a bit more. Um, and in here, this file was 750, 760, something like that. Yeah, 768. Um, so I think you definitely see some difference, and it's more dense code. Um, yeah, I think that's accurate. Um, let's see. The other thing with recursive descent, um, it's less runtime overhead, maybe. Um, the recursive descent, I mean, it's basically using the computer stack to call the routines, and it checks them. It's just check a token, do this, do the matching, whatever. This one has more overhead because the parser library is, I don't know, if you were around for any of the debugging, you're going through all the pieces of the parser, okay, and instead of just being straight line code that you just go through, you're removed a level and you're trying to kind of find your way through an or nested in an and nested in an or next to an if next, just down and down and down. Um, so there's some difference there. The performance seemed comparable for what we were doing. I mean, our 300 tests ran in about a second, maybe once that was warmed up. I don't know. We'll see what they're doing here. This one is I don't know if I want to say it's more flexible, but let's see, how long was that? 0.586. I mean, we were running mostly around 1 second. I don't know if that's a reflection of the slowdown or it's just kind of random how long they take. But, we got 300 tests in less than a second. It's zipping along pretty good. I'm not too worried on either case. The thing that's there, though, in a way, this has I would say it's easier to break out of the parsing model for weird cases. Okay. And this one, it enforces a grammar style and working around it pushes work into semantic routines, into semantic functions. Okay. So an example maybe trying to think what I would say would be an example. Maybe the unary minus or something like that. We can do things. I mean, we have access to the whole input, and we kind of more explicitly know where we are in the code, and so we can put little checks in that, like the minus one. I think like knowing whether it's a unary minus or a binary minus, in a way, is, I don't know. It just feels like we can do stuff in the code that's easier. And this one, like here, when you build up the, let's see, the recursive descent thing we just showed. Okay, this code, it's, notice how many expressions it's keeping, right? It's only looking at one at a time. So it builds a term and then combines it with this op2 result right away, and then the result is the last term it built. So at any given moment, there's only one result that's going to be returned. The rule for our branch, our combinator version, it actually parsed this and got a list of expressions out, and then you had a routine that knew to run through the whole list. So this one only ever built up one at a time. The the parser combinator builds up the whole list and then runs a routine that runs over the list. And that made some trickiness. Yeah, it just pushed a little more work out there into maintaining the list of things and a little more overhead. Then the last one, I guess, is debugging. Debugging is easier. Debugging is a pain. Okay. Maybe I should do something before debugging. Maybe that's the last one. Just in terms of understandability, each routine is, how do I want to say this? Hey, routine types are simple. Implicit input to expression or statement. And here, the parser types get complicated as their compositions of all internal parsers. It's kind of a mouthful. But what, let's see, let me go back to the code and back to the branch. Check this out. Okay, so let's find. Let's open up expression parser. Okay, so expression parser, recall, is got all the pieces of expressions reflecting the precedence levels and so on. Okay. The type of the whole result expression parser, we return it, so it's up here, is bind token expression. But if you look at what's really going on, okay, the question I would say is like, what's the type of this? Okay. That's the type of this. Okay. It's reflecting every parser all along the way, all the 9 levels that went into this. And so it's a check of a separated by of a check of a separated by of an or else of a pipe of an and then tuple of them, any one of a satisfy with a check of a pipe and I'm surprised the Swift compiler can keep up with this. And I suspect, like 5 years ago, it probably couldn't. The reason I think it is better at it now is the Swift UI user interface package depends on this same sort of extremely deep type nested kind of stuff. I tried playing with the sum keyword because I feel like I should be able to say this thing just produces a parser. You don't care what the types inside are. You just care it's got the right method to call parse on it. That's like the only thing it promises. And I couldn't get that together. I suspect somebody who knows what they're doing probably could, or it may be like the next version of the language, which is actually in beta at this point. They have done work on any and some, so you can say any parser or some parser, and kind of throw away the need to maintain all this stuff. Now, when you're debugging, this is the stuff you're debugging through, so that's why I say it's really a pain to debug, because if you want to get down to this, matching this particular token with the satisfy, you're going to go through all those nested steps all the way up. Okay, so it's quite a difference, compared to the recursive descent form is just, method, returns, type, or throws. Okay, and that's it. And this one doesn't do any of that, and it doesn't throw. It builds this sort of functional approach. This is maybe a what would you call this? this is a functional approach. I definitely can say that here. And this is a well, it's almost like a structured programming approach. Maybe that's not quite the right phrase for it, but every rule of the grammar turns into an if, a while, or a sequence of potentially sorry, let me save anyway. If whatever, or while, if, while, or sequence of potentially recursive routines. I mean, it's very much structured programming style. You didn't see a lot of go-tos or anything like that. You did see some weirdness around error handling. The throws is a little bit of a break from pure structured if, while, or sequence. But it pretty much fits in that style. It's almost a transformation from the grammar to structured programming is kind of what that really is. And this one is much more defined functions. So all our parsers, they're either base level parsers or they're parsers that are functions that take other parsers and combine them. It's very elegant, but it's a pain to debug, and the types are complicated and so on. But when you're just looking at it as a grammar, oh, it's very sweet. You know, it's like match this, match that, pipe it to the semantics and go. And that's all, you know, when it works, it's beautiful. All right. Okay. So where does that leave us? Okay. So on the whole, I think the combinator approach is an improvement. If you're extending it, I think mostly, like, I could imagine there are definitely some basics out there that let you do string addition. So $A plus B is string concatenation, and this thing would do that. Oh, I should mention one more thing. I guess I'm gonna have to insert a line. Another thing that happens is this is straight line code. In effect, this one allows backtracking. Maybe that's the thing I should say. No backtracking. Commit to a rule based on the next token. Okay. This one, the combinator approach, does allow backtracking. We used it in a couple of places. A couple of places it made things harder for us, but it does allow it. The place we could use it, we had we had the if then. So you had if this then 5, meaning go to 5, or you could say if this then print something colon do something else. They both share the same prefix, so you could deal with that by backtracking. So it allows more flexible grammars, basically. We didn't make much use of it in the end. I think I peeled out all the ambiguities that would need that, but it's there. And that means you can kind of swiftly get a grammar up and, you know, write it very much written in the style that a grammar writer would write, and then go back through and find those places that needed backtracking and reduce or remove them if you wanted to. You know, more work, but you have the option. So it allows a little smoother transformation from the original grammar to the compiler grammar. Okay. All right. So with that, anyway, I think the combinator approach worked for us. I definitely learned a lot about combinators compared to where I was 6 months ago, and took an earlier stab at it. I think I have a pretty good picture now, at least how that works for us. There's still more for me to learn for sure, but I've got working code to show for it, so that's something. And that's been pretty good. All right. So thanks for joining. I mean, we did I don't know, it was a couple months to write the basic interpreter and a couple weeks worth of transformation to switch the parsers out. My plan is to explore a different way of switching out the parsers next time. So I'm going to go back to the main branch and split off a different variation that uses more of a plug-in strategy. So You can select the old parser or the new one, and just so we can kind of compare what's it like to evolve one way or the other. I may steal a little bit from the evolutionary design we took, but mostly I want to get a feel for that plug-in kind of nature of things. And once that's done, that'll be probably, I expect that to take a week or two, not any longer than that, I wouldn't think. I mean, it shouldn't take any longer than this evolutionary approach, really, but we'll see. I'm going to put a couple constraints in and maybe see if I can make it a little more interesting, realistic for other situations. But that'll be a good exploration of these two things. So I'm not exploring compilers so much as I am evolutionary design and ways to deal with that. So we'll pick up with that starting Monday the 29th. All right, so I'll stop here. Thanks so much for joining, and I hope I catch you in the future. Have a good week and good weekend, and take care. Bye-bye.